When we apply conservation of energy to heat energy, the concept still works. Kind of like we've done in the past, we're going to assume that it's 100% efficient, that all the joules that left the material that started hot were given to the material that started off colder. When we write it out in math, really what we're saying is that one of the materials, my notation's not going to be great, but I think it gets the point across. One of these materials cooled down, therefore it lost joules of energy. If we compare that to the one that warmed up, the one that warmed up gained joules of energy. The one that gained energy gained as much as the other material lost in terms of joules. The material that lost energy, when we calculate the Q, we're going to get a negative value for Q. The one that gained energy, we're going to get a positive value for its Q. And it just works out that the joules are conserved, so the negative value that was lost is exactly equal to the positive value that was gained. For this particular one, there's a lot going on in the question. Here, I'll highlight the one that lost. So the mass of the one that lost energy, it started off at 250. Temperature-wise, it went from 100 all the way down to 22. And the point of this question is we don't know the heat capacity. So when we set up MC delta T of this one, I'm going to say this was the lost. When we set up MC delta T of this thing that lost energy, the mass is 0.25. I don't know C. The change in temperature is always the second minus the first. So in this case, it's going to be 22 because it ended up at 22. Take away 100. That's going to flip to be a negative number, which is okay. We're kind of expecting that since it lost energy. The other object, the one that started off cooler and ended up warmer, we read through the question, it was 2 kilograms that started at 20 and ended up at 22. It says that it's water, so you don't have to memorize numbers. I didn't type it in here, but we know the heat capacity for water. The M in the question was 2. The heat capacity for water, I'm going to use 4,200. The change in temperature for the water, always second minus first, 22 minus 20. All that should combine to make 0. If I clean it up, the 22 minus 100 is negative 78. We have to multiply that by a quarter. This first term turns into 19.5 times C with a negative sign. The second term, the 4 times 4,200, sorry, the 2 times 4,200, but then there's another 2 back here. Really, it ends up being 4 times 4,200. That ends up being, I got 16,800. Those two combine to make 0. If we do a little algebra, got to subtract the 19.5C to the other side, then divide both sides by that 19.5. When I do the math, I get the heat capacity of this unknown metal, when I round it off, is 862. It carries the units of joules, kilograms, degrees Celsius. That's how we can use conservation of energy with heat energy.